Science is often described as a search for truth, a steady accumulation of knowledge, a method for proving things about the world. But what if science cannot prove its theories at all? What if the strength lies not in confirmation, but in systematic doubt? In the 20th century, one philosopher reshaped the foundations of scientific thinking by proposing a radical idea. Science advances through falsification, not verification. And at the heart of this vision lies the powerful logical engine, deduction. Suppose you observe 1,000 white swans, you might conclude all swans are white, but no matter how many confirming cases you gather, you can never logically guarantee the universal claim. Yet a single black swan is decisive. This reveals a logical asymmetry. Universal statements cannot be conclusively verified by finite observations, but they can be conclusively falsified by one counterexample. This asymmetry between verification and falsification forms the logical backbone of falsificationism. The philosopher Karl Popper developed this view in explicit opposition to the logical positivists of the Vienna Circle. In The Logic of Scientific Discovery, Popper rejected the idea that science proceeds by induction, by generalizing from repeated observations. Instead, he argued, induction cannot be logically justified. The problem traces back to David Hume. Hume showed that any attempt to justify induction assumes that the future will resemble the past, but that assumption itself cannot be proven without circularity. Popper accepted Hume's skepticism, but instead of despairing, he proposed a different model. Science does not infer universal laws from observation. Science proposes bold conjectures and then attempts to refute them. Scientific method, in Popper's view, formulate a bold universal hypothesis, deduce observable predictions, test those predictions, if falsified, reject or revise the hypothesis. No induction required. Deductive reasoning follows this valid structure. If T is true, then P must occur. Not P occurs. Therefore, T is false. This is an instance of modus tollens, one of the most secure forms of logical inference. Unlike induction, which is ampliative, extending beyond given premises, deduction is truth-preserving. If the premises are true, the conclusion must be true. For Popper, this meant that falsification is logically decisive, at least in principle. Scientific theories are universal statements. Universal statements entail specific predictions. When predictions fail, the theory collapses. Science progresses by eliminating error. Popper emphasized that good scientific theories are risky. A theory that allows almost any outcome forbids nothing and risks nothing. The more a theory forbids, the greater its empirical content. For example, it will either rain or not rain tomorrow. Unfalsifiable, trivial. Light will bend exactly 1.75 arc-seconds near the sun. Precise, testable, risky. The latter makes a specific prediction that could be falsified. Scientific progress, therefore, is not about accumulating confirmations. It is about increasing empirical boldness. But here, the elegance of Popper's model meets a complication. When a prediction fails, what exactly has been falsified? A scientific prediction rarely follows from a single hypothesis alone. It depends on auxiliary assumptions, background theories, instrument reliability, experimental conditions. This insight is associated with Pierre Duhem and later extended by Willard van Omen Quine. Experiments test entire networks of assumptions, not isolated hypotheses. If a prediction fails, scientists must decide, reject the core theory, adjust an auxiliary hypothesis, or blame the instrument. Falsification, therefore, is not purely mechanical, it requires judgment. Popper himself later acknowledged these complexities. He distinguished between naive falsification, immediate rejection after any anomaly, and methodological falsification, where theories are abandoned only when a better alternative exists. Scientists tolerate anomalies, they refine models, they protect core theories when doing so increases explanatory power. This aligns more closely with later philosophers like Imre Lakatos, who described research programs with hard cores and protective belts. Scientific rationality, in practice, balances logical rigor with pragmatic strategy. Falsificationism reshaped our understanding of science. It rejected certainty. It rejected induction as justification. It embraced deduction as a tool of criticism. Science, on this view, is not a fortress of verified truths. It is a dynamic process of bold conjectures exposed to relentless testing. Its strength lies not in proving itself right, but in designing methods to discover when it is wrong. Deduction provides the logical structure. Falsification provides the methodological courage, and together they form a vision of science grounded not in certainty, but in disciplined risk.